so welcome back to the post-coffee break session. So we have Joost-Pieter Katoen, who's going to talk about parameter synthesis and probabilistic models, a general survey. And I guess we'll have another talk in this session before lunch.
Yeah. Okay. Thanks a lot. So my topic is about probabilistic model checking, and just in a very brief way, what is probabilistic model checking? We start with a model that also includes some probabilities, typically finite state. We have a certain property, and then we're analyzing basically what is whether this property is satisfied. And the property is typically something like quantitative. So this says something like with probability at most 0.1, eventually we will reach a fail state. Okay. And this has been completely automated, and the core of model checking is basically computing reachability properties or probabilities. And I will use this as a running example throughout the talk. It's a very simple Markov chain, 4 states. We want to reach the green state, and we start in S1. So how are we typically tackling this? We are checking whether this state is reachable with a probability, let's say at least 3/4. So what are we setting up? We're basically attaching to every state a variable, and then we're asking ourselves, well, the probability to reach the green state from 3 is 1, so therefore we set this variable to 1. From that state, you can never reach the green state, so that's set to 0. And then for the middle 2 states, they are the most interesting ones. You set up an equation in terms of the other states, right? And that you can solve, and this is actually a system of linear equations. And actually, you can prove that this has a Unix solution. Good. So that's what it was all about. So in some sense, probabilistic model checking in one line reduces to solving linear equation systems. And now you might ask yourself, what happens if I have omega regular properties? What happens if I have a probabilistic version of CTL? In the end, the core is, again, computing reachability. For Markov chains or for MBPs, for more rigid models. But that's basically it. Yeah. And this you can do quite efficiently, right? And then because what you check at the end is you check whether, in order to this specification, you check whether P1 is at least 3/4. And this has been implemented in several tools. There have been two competitions. Here are the results of 2019, where on the x-axis you see the number of instances you solve, and on the y-axis in log scale, the amount of seconds that in order to solve these issues. And we developed this model checker called Storm that we basically started 5-6 years ago, that actually analyzes these models pretty fast.
What's the difference between these 4?
So the most well-known model checker is the green one, which is Prism, developed in the group of Marta Kwiatkowska. So actually what we did is, but that's, I mean, I would say algorithmically, we're not doing that much different than Prism. But we started 5-6 years ago and basically, looked a lot at what are the, let's say, the critical operations in model checking. And we set up the model checker in a modular way. And I think in my interpretation, Prism suffers from the legacy of 22 years developing an add-on and add-on and add-on. And Dave Parker, he's not here, but he told me that there are about 27 implementations of solving linear system equations in Prism. We only have 1.
But are you using linear equation system solving or value iteration?
There we use value iteration.
Okay.
Yeah. But that's the same as Prism. Yeah. And the other model checkers, one is developed in Twente, which is MCSTA.
What about this modest? What is modest?
That is this. And this is MCSTA. This is the blue one. Yeah. And the orange one is a model checker developed in China. Yeah. Focusing on LTO. Yeah. Basically, same principle. The underlying principle is solving system of linear equations. How you solve them and how you get to them, there are different ways to do that, but conceptually it's the same.
How large are these instances? How many?
These instances, these benchmarks are not particularly very large, but you think about millions of states, 10 millions of states, 20 millions of states. That's not an issue. Yeah. Actually, the size of the probabilistic model is not the key component. The key component is the ratio between the smallest and the largest probability that occurs in your model, because that says something about the convergence of getting to such a solution. It's not the number of.
And what is the worst ratio in these cases?
Oh, I don't know. I have to look into those benchmarks. I don't know the problem.
You need to do optimization for
Yeah, sure. You can do various optimizations, right? I mean,
it's not just solving this equation.
no. So if this would be an MDP, if this would be a model with non-determinism, you don't have a linear equation system, but you have a linear inequation system. And basically, what you have to solve is a linear program. Yeah.
So that's what you're clubbing in all of that.
Yeah. I'm going to talk here today only about Markov chains, but almost everything I said.
Because you want to get to the parameters.
Yeah. But everything is also almost everything applicable to N. Yeah. So this works, and also MDPs, and this works. Actually, even for models of billions of states.
And also continuous time.
Also continuous time. There are even people working. There's a version of Prism Games. I don't want to give here a whole talk about probabilistic model
We
checking.
want to get to
The whole point is that all these probabilities need to be known a priori. Yeah, in your model, you need to know that every transition has probability a half, a quarter, and so on. And that's something that is not always very useful. And I'm going to motivate this by what I call how to pick the optimal bias. And we're going to look at self-stabilization of a distributed system. Now, self-stabilization has been well studied. And Dijkstra has a famous paper in '86 where he says that if you have an anonymous network, that means if you have an algorithm that cannot use the identity of your processes, right? That doesn't need anonymous, then self-stabilization is impossible by a deterministic algorithm. And then Ted Herman said, yeah, I can solve this problem for you, Dijkstra. I'm going to use randomization. So let's have a look at how he solved this. And that's actually a very nice algorithm. So the algorithm is in a ring. So here is a ring. It has an odd number of processes, and every process only has a Boolean variable. That's it. So you know your own Boolean variable, and you have access to the Boolean value of your left neighbor. Okay, so this process, number 0, can see the value of the left neighbor. My values are the colors. Okay, good. And then there are so-called tokens. And a process has a token if its value is the same as the left neighbor. So in my picture, if your color is the same as your left neighbor, then you have a token. Okay, good. So now the whole algorithm is a 2-line algorithm that says for every process does the same, right? It needs to be anonymous. And it basically says if your value is the same as your left neighbor's, then you're going to flip a coin, which has a bias of P. And you set it to 0 with probability P and to 1 with probability 1 minus P. If your value is different from your left neighbor, you copy the value of your left neighbor. And this is the whole algorithm.
So that means if you have the token, you relinquish it with some probability.
If you have the token, you're going to flip your coin. Yeah.
And if you don't have,
the token, you just copy the color of your left neighbor. That's it.
And then you may have.
And then you may have the token, depending on the outcome of the coin flips. Yeah.
But I don't see anything about having the token, passing tokens to.
No, token means
So token is simply the same.
Token is simply the predicate.
Okay,
I have the same value as my.
So it's not that there are two tokens.
Good. And this is then you're interested in, and that's what it is. You possess a token if your value is the same as your left neighbor. And now the performance metric is what is the expected number of steps until convergence? What is convergence here? There is one token in the whole metric. Okay. Good. And this is self-stabilizing, so it must basically. So if you look at one computation, let's suppose this is my initial configuration. As Shankar already pointed out, all the processes without a token just toggle that color, because if you don't have a token, you take the color of your left neighbor. So this process is red, but its left neighbor is green, so this toggles the color. Yeah, it inverts its bit, so to speak. And now you can think about all the processes that have a token, this one, and that one, they flip a coin, and based on the outcome, yeah, they can either, let's say, change the color here from green to red, or this one is green and remains green. This is possible, depending on the outcome of your coin flip. And now you have to reassign the tokens, because now you have to basically say those people those processes that have the same color as their left neighbor, like number 2. It doesn't have a token before, but now it has a token. And now you see that basically we did not make any progress because we had 3 tokens here and we still have 3 tokens. But of course you can imagine
I need to put this in which way.
this is
Okay.
zigzag.
Yeah.
Z.
Yeah.
That's the way to do it. But it's one step. I divided into sub-steps, but that's one step. And now the question is, how many steps on expectation do we need until we get a configuration with a single, let's say, token?
Or isn't it so that you have n tokens? You have the token if you have the same color.
You have the token only if you have the same color as your left neighbor.
Then they should all have the token.
No.
No. If they all have the same color, if they all have the same color.
Now you need 1 token at the end. That's the way you will do it.
That's not stable.
So imagine in our alternates and then just 2 of them, because it's all 2 of them have the same.
But you need them all to have the same color.
No.
Just one has the same color as its.
One has the same color as left neighbor, all others have different colors as the left neighbor. That's the stabilization.
Okay.
That's the stabilization control. Yeah.
That's
Good. And now if you analyze the protocol, here is a plot on the x-axis, you see the probability, the bias of your coin. And here you see the expected number of steps until the algorithm converges. Okay. And now you can look at several ring sizes, and those are the different colors of my plots here. And now you see the interesting phenomenon that for small rings over here, a fair coin is optimal. But you see if the ring becomes larger, actually you see that you have 2 optimal. Okay, and we analyzed this protocol by means of, we modeled this by a parameterized Markov chain. Yeah. And now you analyze automatically, you synthesize the optimal values of P. So these dots are automatically synthesized. So not by model checking many instances where you vary P, but you really take P as a parameter and you try to determine what is the minimal value of P, or the optimal value of P that minimizes the expected recalculate. Question?
Yeah, so does this, you get these curves from some analytical expression?
Now, I get to this.
Okay.
Yeah. So this is my motivational example. These kind of protocols I like to analyze, these kind of problems I like to analyze. Now, this is a simple example. I have 1 parameter. What happens if I have 20 parameters? Yeah, but this is what I would like to analyze.
This is so that you actually have 2 parameters. There's also in.
Sure. Yeah. But I'm focusing here in my talk on the parameter P, not on N. Okay? We're going to fix.
Then you're in that.
We have a fixed number of processes, but P is a parameter.
Yeah.
Okay?
And is there an intuitive reason why this 1 optimal changes to 2 optimal?
No, we will have to listen.
Yeah. Yeah. This protocol is very difficult. If you look at the literature, there are many papers that try to analyze this Ted Herman's probabilistic self-stabilizing algorithm. There have been conjectures about this, the number of iterations for even for the fair coin is very. It's not so easy. So it's not easy to answer your question. It's a very intricate, interesting. Good. So this can be automatically synthesized, and now I'm interested in what's the underlying theory, what are the algorithms, what's the complexity, does it scale, and so forth. Okay. I'm not getting through all the end, that's for sure now after all these questions, but let's see how far we get. Good. So the model that we're going to take are parametric Markov chains. So what are parametric Markov chains? Here you have an example. This is here I use 2 biased coins to mimic a 6-sided die. These are the possible outcomes. Here I flip a coin. With probability X, I go to the left, with probability 1 minus X, I go over there. And in those 2 states, I pick another coin with bias Y. So with probability Y, I go here, with 1 minus Y, I go there. And here, apparently, I use the same coin as in the beginning. I use X and 1 minus X. Okay, good. So this is these are the parameters. And then what is a parametric Markov chain? We have a finite state space, so no N, Kim. Finite state space, we have a finite set of real value parameters, in my example, X and Y. And we have transition functions that map pairs of states to multivariate polynomials over X. In my example, P1 minus P, but there could be whole polynomials. How do I get a picture like this? Well, that's very simple, right? I just instantiate x with a certain value and y with a certain value. So that's my valuation x or v. And notice that this allows for parameter dependencies. You see this x occurring here, but it also occurs there. If you now would like to, for instance, maximize the probability to go here, it might be good to have a high value of x here. Well, suppose that we have to go to 2 and maybe a low value there. So you get dependencies. You get trade-offs. Yeah. Good. So a few notions I need. So I'm going to use this as notation. So what is D is such a parametric Markov chain with n variables. I'm going to use a specification. So this specification is, for instance, is the probability to obtain a 2 as outcome of my 6-sided die satisfies a certain threshold. And then what I have is if I suppose I have 2 parameters, then you can envision that we have a parameter space in 2 dimensions, the y dimension and x dimension. And now I give you a region. What is a region? Pictorially, it simply means a kind of a rectangle, which is part of my parameter space. And now I'm basically saying that my model in that region satisfies a specification if for all valuations in this rectangle, uncountably many, right, valuations, satisfies the specification. Okay, which is here not the case. That was a valuation. So this is one valuation, it's 1 point in this space, right? And what is the instantiation? The instantiation is you give me such a parametric thing and I replace all the parameters with the values indicated by D. So D of V is really a Markov chain with all fixed probabilities, but D is the one with parameters. Good. So the first question I'm going to address is there one valuation for which the specification is satisfied? So find one green point. Good. So let me address this, and let me first address the complexity. So I go back as the same example as before, but now you see that now my probabilities are x and y, and 1 minus y and 1 minus x. But exactly the same question, I want to reach the green state with probability at least 3/4. So we're going to do the same. I'm going to assign variables to states. So I'm going to ask, does there exist, let's say, values of these introduced parameters and the parameters in my model, such that the following holds. Well, I mean, those values of x and y should be between 0 and 1. I don't allow to erase transitions. Okay, so that's why I strictly allow x to be strictly between 0 and 1. And then I had a specification. So initially, I would like to reach the green state with at least 3/4. And for the rest, I set up an equation system similar as before, with 1 for 3 and 0 for 0. And for the other ones, I get a nonlinear equation system, because now I get something which is parametric in the p variables, but also in the x and y variables. Yeah. Okay. This is here. And actually what this is nothing else than a formula in the existential theory of the reals. Okay.
So would it have mattered if you had allowed erasing transitions?
Yeah, it matters. It matters. Yeah. Yeah, it's quite, it matters because you get certain discontinuities in your functions that we're going to see later, if I get to this. That's really a different thing. So it's important that the valuations are what we call graph preserving. You don't change the topology of your model, but you only change the values. Yeah, good point. Good. Now I'm going to show you that actually any ETR formula can be cast into a reachability probability in a parametric Markov chain. Okay, so and I'm going to do that by means of an example. So it's existential theory of the reals.
Okay.
Yeah. So let's look at this formula. There exists an x such that this formula is at least 5 has a solution. That's the question that is typically an ETR sub kind of formula. And now what you can do, you can massage the formula a bit. And believe me, this is a correct transformation. So this has a solution if and only if that has a solution. Okay. And now I'm doing the following trick. I'm going to rescale all the parameters. And such that here, I mean, I bring this 2 to the other side. So this becomes 7. And now I divide everything by 8. Okay.
So is this a solution preserving transformation or just satisfying?
Yeah. The solution preserving transformation. Yeah. I'm losing nothing in the transformation. It's really equivalent. Yeah. It's really if and only if, the red bars. And I hope you can also see that this is even only if, right? Because the only thing I did is I brought a 2 to the other side and divided by 8. And that's
It's a little bit more tricky to check out the polynomials.
Okay, but now what you can see is that you can convert this now into the reachability probability into a parametric Markov chain. At least 7.8 becomes my threshold. Yeah. And now you see that this polynomial 2 over 8 1 minus x is 2 over 8 times 1 minus x times y. Yeah. So basically these polynomials are encoded as sequences of transitions in my parametric Markov chain. And the plus are the branches. Yeah. Here I got 1, 2, 3, 4 monomials. So I get 4 branches. And you can do this for every ETR formula. What did we see? We see that the feasibility problem, does there exist a solution for a parametric Markov chain satisfying the specification, LTL, reachability? It's ETR complete. Good. What does that mean? This means that ETR is between NP and P space. What does it mean? It means that this is as hard as checking whether 2 polynomials have a common root, or it's as hard as does a given polynomial have a real root. Okay. Now you can also do this for MDPs, as you asked. What about MDPs? I'm not going into the details. It depends a bit on whether you need strict and non-strict specifications, whether you're interested in arbitrarily many parameters or a fixed number of parameters that you, let's say, you give me up front. But basically what we have seen was this, and you see this also carries over to parametric.
So what if you were only allowed to use parameters a single time? So you
Yeah,
didn't have to
that's way easy. Yeah.
So yeah, I mean, like, do you know, is it polynomial or?
Yeah, but I think that even for async, yeah,
I think it was take this on.
yeah.
So because you're exploiting the dependencies here,
Yeah.
this was present in your.
I'm not sure what happened now, but something happened.
You went out a slideshow.
Yeah. Back easily back.
There's something called play there.
Yeah, we're back again. Sorry for that. So this we just saw. Okay. The second problem I would like to address is what is called exact partitioning. What does that mean? I want to split the parameter space into the satisfying valuations and the refuting valuations. Okay, so in terms of the picture, I'm looking for this curve. Yeah. Good. So how can we do this? Well, same example as before, for which is can we reach the green state with probability at least 3/4? And now what you need to solve is exactly the nonlinear equation that we have seen before, right? Plus, and that's what you can just solve, and that you get this rational function. Okay? So basically, what I'm doing here is I'm basically solving a system of linear equations, but now over the field of rational functions, and no longer of the field of real numbers. Yeah, no longer over the field of probabilities. Okay, so it solves a nonlinear programming problem. That's what you can do, but there is a more efficient practical method, and this is called state elimination. I get to the complexity in a minute. So what is state elimination? And now you read the pictures from the left to the right. And the pictures are fragments of the algorithm that you have seen before. Now they're called P and Q and not X and Y anymore, but it's the same. So what are we going to do? The first thing what we are going to do, we're going to remove a self loop. So what does it mean if we remove the self loop here? We're going to rescale the probabilities of the outgoing transitions. Why can we do that? Because it's a geometric distribution on staying here. So in the end, what you need to do is you divide all these outgoing transitions here with 1 minus this probability at the self. Now I can remove S1. That's what we're going to do now. What does that mean? It basically means that we're going to multiply the polynomial, the rational function, which is here, with the rational function over there. And that becomes the rational function on the arrow that goes directly. And we can repeat this. So now I can remove S4. And now in the end, I have a picture like this. And in the end, what you get is basically going from the initial state to all possible target states by one transition. And basically, it literally removed everything in between. And now you can just read off this equation. If I'm interested in what is the probability to either end up there or end up there, you just add those two rational functions. And that's it. And then you ask something like this. And if you say, well, this is very analogous to obtaining regular expressions from NFA, this is indeed the case. So the order in which I do certain things is important. In the worst case, your polynomial gets very, very, very big and so on. But it's in practice way much faster than solving the system of equations. These are the kind of polynomial functions you get out of it. It's similar to the picture that you had for the call graph. If you zoom in, you get things like this. Very big coefficients, but also very big, y to the power 11, x to the power 10, blah, blah, blah. And this is for a very small model, just 40 states and 2 parameters. So can we say something about the size of this polynomial? Yes, yeah, you can. You can get an exponential growth, and you can see this by means of this gadget. I want to reach the green state. And what you see is that in every possibility, you go with a certain probability 1 minus x1 to the next thing, and then you are still on the way to get the green. But there also is an option at every stage to opt out and immediately go to the red state. From the red state, you will not be able to reach the green state. Good. The reachability probability of this thing amounts to this. Well, definitely you need to go through this whole sequence. So this is this product. You can rewrite this product a bit. What is the problem of this product is that the shortest sum of monomial representation has 2 to the power n. So exponentially many monomials in the number of parameters. Okay. And this gives rise to the following complexity result. It says that computing such a rational function only for reachability is already exponential in number of parameters. It's polynomial in number of states, so the number of states is less relevant, but it's also polynomial in the maximal degree of the polynomial transition function in your map of G.
But it seems that the product of these 1 minus xi was also a good representation of that function in that small.
Yeah, but you need to multiply the whole thing, right? Or was there multiplication?
Well, I just say 1 minus x, 1 times 1 minus x. So why is it's because you want some monomials.
Yeah. Yeah.
But you could just stay with this.
Yeah, but then you have to manipulate this, right?
Depends on what you want to use it for.
Yeah.
If you want to find roots, I prefer the first.
Yeah.
I prefer the first expression.
Yeah.
It's almost like doing a product. I mean, doing the expansion work.
In a sense. I'm going to skip a couple of slides because of time, I think. So I would like to address a bit algorithmic approaches to get here I've shown you that this is ETR complete to find such a point, and now I would like to show you how you can basically algorithmically deal with this. What we're going to do is basically there are several approaches to this. So one is basically take the ETR formulation or the solution function I've just shown you. This is very exact. So this is a level of exactness. It's very exact. It's precise. Of course, you can do things like simulation. I mean, I'm interested in only finding one instantiation satisfying my specification. You just sample. That's a possibility, and you can do clever things like particle swarm optimization, but it's not very precise. I'm going to show you an approach in between, and the approach in between is going to use mathematical optimization techniques. Actually, what we do there is we use what is called sequential complex programming, and sometimes also complex concave procedures. Good. So what's the principle, ladies? And I'm going to use the same example as before. I think the only thing is I now at most 3/4, but for the rest it's the same. So the thing is that we're going to cast this as an optimization problem. And I'm going to sacrifice, let's say, exactness. I'm interested in epsilon optimal solution. Okay? Because the exact solution was ETR. Yeah. So I'm going to give up this, but I'm going to do this approximation. So we're going to do the same as before. This is the specification. From P1, we need to reach the state with composed of 3/4. We have these equations before, they now become inequations. And we would like to minimize P1 such that it satisfies this objective function under all these constraints. And in addition, we would like to be epsilon approximate. So it means that for P1 and P2, it's okay if we're epsilon after the real solution. Good. And this is actually a quadratically constrained program. Quadratic because of these quadratic constraints over here. So this you can solve as a QCQP kind of problem. That's still not very useful. So the next step that people typically do in mathematical optimization is to actually linearize these polynomials. So linearize these quadratic constraints. And what you do is you basically take this a value of f by taking the value of f in a certain point, plus you take the gradient. So you look at how much it's changed. Let's say, with respect to a certain point. This point is the head thing. The head thing are concrete values. So in my case, for instance, the head thing could be is a value of x and a value of y. So values of those parameters. And the same for the P1s and the P2s. And those were the reachability probabilities for the two states. And now that was the minimization problem we had before. And this was a QCQP problem. And now if you do this gradient technique, what you see is that in particular, those two constraints over here will change because you have to, let's say, take this gradient. So now you get constraints that look like this. And what you see is the quadratic thing disappeared because here you had something of the form x times P2. Here you still have an x, but x is only multiplied with values with a head, and head are concrete values. Yeah. So you actually transformed a QCQP problem into a linear programming problem. Yeah. And this is what you can solve. But people in optimization also know that you have to be a bit careful because now the question is a feasible solution here also a feasible solution there? This is not always the case. So what they do is they use what is called penalty variables. So it means that actually what you're going to do is you're going to add two variables in my case because I have two unknowns, P1 and P2. We're going to add two penalty variables, K1 and K2. You add this to the objective. And what you do is you also add them here. And the advantage of doing this is that you get basically carry over solutions from the equation system on the right-hand side to the equation system. This is still a linear program. It's also a linear program. To ensure that the linearization is accurate, there is another trick, trust regions. I'm going to skip that here for the sake of time. So what we're actually doing is the following, and this is the approach that we recently proposed in a 2022 paper in RWTH. So what you do is you make an initial guess, and then you convexify over this guess. This was my gradient computation. Yeah. This gives you a linear programming problem to solve it. And now you have to check whether the solution that you computed is a real solution. And how are we going to do that? Well, we're just going to apply model check. Because in my case, an instantiation is a real Markov chain, right? And I can just model check this Markov chain. So this is something that you can use because of you exploit the fact of your application domain, so to speak, of the mathematical optimization problem. If this is satisfied, then you found the solution and you can return the valuation that you tried. If that's not the case, then you basically have to go back by widening the trust region and by maybe updating your valuation, and you try to do that again and again until you get a solution. Okay, what is beta? This beta is the value up to so far. Okay, it starts initially with 0, and I think here you basically update beta, and this means that this is the current value. So you update. Yeah. So beta is the value up to so far. Yeah. This has been, this by the way is also applicable to parametric NDPs, and then you get any equation system, but the same kind of scheme. So what we see here is a tight interconnection between, on the one hand side, mathematical optimization, on the other hand side, model checking. And I'm going to show you what's the effect of doing this check. in a minute. So here you see some experimental results. On the left, you see different case studies with different specifications, with thresholds. P stands for reachability probabilities, E stands for expected rewards, so cost. So this is the model sizes, number of states, number of transitions, number of parameters. Remember, we're trying to approximately solve this ETR complete problem. And this goes up to a few hundred, 1,000 up to 12,000 parameters, quite a bit. And this is what you do if you just do simulation. And what you see is that you get many times a timeout because you take the wrong sample and then your PSO is trying to get to the right value, but it needs many iterations to do that. So that is not good. This is using the combination of mathematical optimization, so this sequential convex programming plus model checking. And you see this is the amount of time, this is the number of iterations of the loop I showed you. Yeah. And then you may ask yourself, what is the gain by using model checking here? Why can't you just not use sequential convex programming without model checking? And if you do that, you get basically this column over here. So you really get orders of magnitude improvement because we have a very efficient way to check whether a found solution is really a correct solution or not. And that helps a lot. And this is one of the problems that people, let's say, in this convex programming field typically have. So this really pays off a lot if you compare these columns with this.
What do you gain from? You learn anything from the failure of the one thing?
You learn a bit from the failure of the model checking, yeah, a bit, but not so much. Yeah, but it's basically the quick and guaranteed check on the feasibility of your solution that helps you out. Yeah.
Could you then add that to these other methods? Since they're not. But I guess there's no loop there that you can fit into.
No, I mean, exactly. It's the iterative approach. It's the iterative approach plus the model checking thing that actually pays off. Yeah. Good. Okay, I think I have to wrap up. So if you compare the different approaches, then what you can do is you can do simulation, but that doesn't exploit the model structure. Here you exploit the model structure because that was my nonlinear iteration system I started off. And with the exact, of course, you also do that. If you look at the number of iterations, you basically are here. And if you look at the time per iterations like this, and if you're interested in how many parameters and how many states can you solve, here you are about a handful of parameters. And here you can go up to, well, we saw example with 12,000. Depends a bit on your model. So it's a kind of a good middle ground between, on the one hand side, being let's say having very fast iteration but inexact, versus the very exact solution that we have seen as CTR. I go to the end, and in the last 10 years, I think there is quite a substantial progress in this field of parameter synthesis. In the beginning, models had 10 states with 1 or 2 parameters, and now we have seen that you can deal with much larger models. I showed you the feasibility problem, or is there a compliant instantiation? I showed you the exact partitioning. There are 2 parts that I check out. The approximate partitioning is something I skipped. But the practical feasibility is what I showed you, is that you can there use mathematical optimization. So that's what we try to do. We trying to find the right probabilities in an automated manner. And this is what we, for instance, also apply to Hermann's randomized self-stabilization. There's tool support. And if you're interested, there is an archive paper that was posted, I think, last week or 2 weeks ago. So good, and thanks to all my cooperators in the past. Thanks.
So, any questions?
Could you say a bit about this, the accuracy? I'm not sure I fully understand. You had this line. You made me believe that what you presented with this loop was exact, but apparently it's not. This thing here, level of exactness.
Yeah, the level of exactness,
Exact because you
the
have
more you're on the right, the more exact you are.
Yeah.
I'm not exact because I'm computing an epsilon optimal solution. It's not exact. The ETR
why are you
encoding,
computing an epsilon?
yeah, because
You make this transformation into a linear by
yeah,
having these.
exactly.
But then you had these, you had all these kind of things, these penalization decays,
Yeah,
and
but
it's still inexact.
it's still epsilon. It's epsilon exact.
Okay.
So the ETR formulation I gave you was exact. Solving this rational function is 1 minus x1
And all the other
1
things
minus
were-
x2 is exact.
Yeah.
Here it's not exact.
But introducing these, I don't know what you call these A variables.
Yeah.
Make it more exact or less inexact. Is that a way of saying it?
It's those are tricks, I would say, of mathematical optimization, in particular convexification techniques, right? Because we start with something which is non-linear and non-convex. And what we try to do is we try to cast it into a linear programming problem. And this convexification, these are basically the tricks to make sure that in the end, the LP problem that you solve, is more often finding a feasible solution.
But would you want to combine this? Because you're starting from some concrete value of the parameters. And then you
This is my guess. You start with a sample.
But maybe you could then make another random guess somewhere else.
Of course.
Did you do that? Combining that your random is
Of course, you can try to do that. And that's what you see if you only guess and if you only pick random variables, then actually you are here, right?
Yeah.
And then we have seen
a combination of these two.
Yeah, but then we have seen that's something you could do. But in our experience, this does not work out very well. Because this simulation stuff, if you don't do it, if you really have to steer it.
But it must be critical. What is the initial value? Of course.
That depends on the number of iterations, and here you see the number of iterations is not too bad. Our guesses apparently are not too bad. But you're right, of course.
Okay.
I was going to ask if what if you want to say, you keep saying you can apply this to MDPs as well.
Yeah.
Is there a way of synthesizing parameters and strategies in an integrated way? Or when you say you apply it to MDPs, is that applying it where your property is that the best strategy?
You then synthesize a value of the parameters such that for all strategies a certain property.
But you can't synthesize.
You can't synthesize both at the same time.
Because that's completely infeasible, or because no one can?
There are two versions of it. Either you first iterate over the schedulers or the policies, and then over the parameters, or first over the parameters and then over the schedulers.
So your schedulers might depend on parameters.
That becomes hard. Yeah. But that was the problem I showed you in the table, in the complexity table. That's still ETR complete. You can encode this. It's an ETR complete problem.
Puzzled about how Ted Herman's algorithm solves the problem. Part of self-stabilizing is knowing that you have the unique order of the program. So
This algorithm, right?
Knowing the expected convergence time isn't good enough. You know that there's a bound by which the system will self-stabilize.
So this eventually will definitely stabilize, right? Because of the randomization thing, it cannot be the case that infinitely often you all pick.
You know, you have a bound now.
Well, that's exactly the expected
It's not another
convergence time. Yeah. Maybe you're interested in more detailed versions. What is the probability that my algorithm will terminate or converge in k steps for a given k? Yeah, that's a kind of a tilde distribution. That's not.
At what point does everyone know?
Okay.
It's stabilized.
Yeah, you assume that in the end that you have that you can make a global snapshot. And if the global snapshot says there is only one process that has a token, then the whole thing is true.
You need to do that.
You need to do that, yeah. That's not part of the protocol.